So I mentioned in that last clip, there are going to be coordinates where the concavity of the function changes. Well, those will be the places where our second derivative is 0, right? There'll be places where the second derivative changes from negative to positive or positive to negative. If it crosses 0 on the way through, as long as it's continuous. Now, we can use concavity to get extra information and make our maximum and minimum test easier. So rather than plotting out what is the slope to the left and to the right of our critical point, we can just check what is the concavity at the critical point. So if my function is concave down, and I have a critical value there, that's going to be a maximum. If my function is concave up, and I have a critical point, that's going to be a minimum. So I translate that into derivatives, into the language of derivatives. As long as my second derivative is a continuous function, I can test for maximum and minimum values by first identifying critical points. That's where f prime at some coordinate c equals 0. And I take that coordinate for my critical point and I put it into this formula for the second derivative of the function. If I get a positive value, then that critical point is a local minimum of the function. If I get a negative second derivative, then that is going to be that critical point is a maximum of the function. Let's actually work on a problem now. So here I've got y equals x to the power 4 minus 4x cubed. So let's figure out concavity. Let's figure out where it has inflection points, and let's find its local extrema. So the local maxima and the local minima. I'm not the only one who knows Latin. Okay, so first I need to take the first derivative. Derivative of x to the power 4 is 4x cubed. Derivative of 4x cubed here is 12x squared. All right, and they've gone ahead and factored that for us. How nice. Now I need to take my second derivative as my second step. So I'll take a derivative of 4x cubed and I get 12x squared. I'll take a derivative of 12x squared, I get 24 times x. And again, we have that factorization given to us for right now. I've got my original function. I've got my first derivative. I've got my second derivative. Let's find those critical points. We are trying to set f prime equal to 0. What are my solutions? They've got to be 0 and 3. Again, I just read that off of the factorization here. So I've got two critical points. Next, I'm going to use the second derivative test. I'm going to test for concavity at both of those coordinates. Here, f double prime of 0 is 0. Not enough information. F double prime of 3 is 36, which is positive. So that tells me at least that 3, x coordinate 3, is giving me a local minimum of the function. So the minimum will be at y coordinate negative 27. Now I'm going to need a little bit more information for this x equals 0. Since my second derivative test didn't work out there. Instead, I'm going to calculate f prime of x, the first derivative, for coordinates to the left of 0 and to the right of 0. So to the left of 0, the first derivative is negative. Again, we just got that by plugging in a value into the formula. For values of x between 0 and 3, the first derivative is still negative. So in fact, x equals 0 is not a minimum, and x equals 0 is not a maximum. It's going to be something else, but not a minimum or a maximum. Now, the last thing we want to do is check for concavity. So where are the coordinates where f double prime of x equals 0? Those are going to be 0 and 2. Does the second derivative change sign there? Yes, it does. To the left of 0, the second derivative of this function is positive. To the right of 0, but, left of 2, the second derivative of this function is negative. To the right of 2, the second derivative is positive again. So we have a function that's concave up for a while, then concave down, and then concave up again. So both of these coordinates, x equals 0 and x equals 2, are inflection points. So inflection points can sometimes show up as one of these critical points and look like it's a maximum or a minimum, but not necessarily every single time. Now let's actually graph this out. Here's a graph of that quartic polynomial, and that looks like all the stuff I was describing. We have 2 critical points, right? They'd have horizontal tangent here at x equals 0 and at x equals 3. The function decreases up until x equals 0, then decreases some more, and then it increases from x equals 3 onwards. We can also check the concavity. We've gone from concave up to concave down, and then to concave up again, where the inflection points are 0 and x equals 2. Again, we got all of this based on the formula of that function and being able to take derivatives. And then we did the graph later to verify our calculations. Where we are going is that eventually we will be able to sketch a graph and have an intuitive idea of what that graph will look like even before we try to graph it using computer assistance.